We're going to do some Red Hat now that we're caught up. All right, y'all. So today we're going to do wireless. And we're going to talk about wireless networks, troubleshooting, and configuring. And a lot of this is just knowing the wireless standards. And I don't know. I'm going to guess these are going to be on your exam because they were on mine way back. But now way back when I took it, there were 3 of these. There were, you know, A, B, and G. There's a whole lot more now. So
AC
yeah, there's A, B, G, A, C, A, N, A, X.
and B, or yeah.
There's a bunch of different ones. So
802.11x.
And there's actually new encryption algorithms too. So make sure you spend a little bit of time, especially look at the stuff about this in the, see if they throw a PBQ about stuff about antennas or anything at you. Kind of watch for that because I really don't know. All right, y'all know that we talk about Ethernet, and Ethernet is what? It's CSMA what? Not CA, but
It's not X, that's cellular.
it's
right?
CD, collision detection. Remember, because on a traditional hub, everything's sending at one time, and Ethernet can detect a collision. That's the whole idea behind it.
Oh, it's one of those acronyms.
Right, it's one of those fun acronyms. Well, this is where we throw an acronym that's very similar but a little different. Wireless uses something called CSMA-CA. Wireless tries to avoid a collision to begin with, and it does that by listening just a millisecond before it sends a signal. And it does that by just listening and getting a request to send and then a clear to send. And the original data rate for wireless was just 1 megabit. So basically the way this works, you've got data to transmit. You're going to check the network. You're going to send the request to transmit signal. You're going to wait to see that all the nodes receive that signal. You get nothing back. Then you're going to transmit the data. And then you monitor for other requests to send signals. So when you see a request to send signal, basically you wait your turn. So A was one of the original standards. Interestingly enough, B got to be more popular, even though B was actually a little slower to begin with. Make sure you kind of know just some of these standards that are older that you probably will never use, like A and B, and know what frequency ranges they operate in, and know that some of the new ones can operate in both. A originally, for example, was in the 5 gigahertz spectrum. 5 gigahertz is less congested. There's less things there, but it has a smaller range. You can't go as far on 5 gigahertz. 2.4 is what we ended up being the standard. That's where B landed. And B was the wireless standard that really took off for a long time. 2 for 2.
I know, right?
B is the one that really took off for a long time. And B ran at 11 megabits. The problem with the 2.4 band is there are so many things in 2.4. Almost all of your wireless traditional phones, which I know not a big deal anymore because not everybody has traditional phones, but think about in the early days of wireless, everybody had a traditional house phone, right? Most of those were in the 2.4 range. The big thing that interferes right now that's in 2.4 is Bluetooth. So Bluetooth uses the exact same set of frequencies that wireless B uses. And think about how many Bluetooth devices there are now. So all of that gets mixed in. So the 802.11a standard would go up to 54 megabits. You had 23 non-overlapping 20 megahertz channels, and it used something called orthogonal frequency division multiplexing, or OFDM. And that is the way the frequencies are built out, and I'll show y'all those in a minute. Here's what the B spectrum looks like. B has got 14 channels. You cannot use the last 3 in the United States unless you have a ham radio license. And even then, it's really kind of iffy as to whether you're supposed to use them or not. But and it's just because of the frequencies they fall in. They are in licensed band frequencies. Notice this channel overlap here that they're showing. And the reason they want you to see that, notice that 1, 6, and 11 are the only ones that don't overlap. So if you download like a Wi-Fi analyzer on your phone and run it against our network and look, you'll see that the access points around here try to use 1, 6, and 11. And the reason for that is if those signals overlap, you'll get some interference. So you try to not overlap it as much as possible. And these are 5 megahertz channels. But Wi-Fi still needs 20 megahertz of bandwidth. So you see, even though they're 5 meg channels, they take up more space. So you really got to be careful the way that you configure that. And 802.11b uses something called direct sequence spread spectrum, or DSSS. All right, so N then entered the stage, and N got us a little bit more speed. And within, we introduced something called single user multiple input, multiple output, or MIMO. And you may have seen that on things when you're buying like a wireless access point. It'll show that it's MIMO compatible. Basically, this uses transceivers to send and receive on different channels at the same time, basically bonding the channels to get faster speed. N can use the 5 or the 2.4 gigahertz at the same time. And each channel, basically, you could get up to 288 288.8 megs on a single channel. So you could bond that together and get up to 600 theoretically. So now we've got AC and AX. AC is also sometimes called Wi-Fi 5. It is 5 gigahertz only. And it'll use 80 or 160 megahertz channels. And it does this thing called spatial streaming. And basically, spatial streaming is using the antennas to sort of beamform the signal towards you, essentially, to get faster speeds. AX uses both 2.4 and 5, and possibly the new 6 gigahertz band if you've got equipment that'll do it. To my knowledge, we don't have anything up here that's doing 6 gigahertz. I don't own anything that'll do it. But it was designed to support the Internet of Things. And the idea of 6 gigahertz is to add some bandwidth for low needed devices that don't need to go very far, but you may have a lot of. Think about like if I had tons of Raspberry Pis, they're not going to use, I don't need a gigabit to go to a Raspberry Pi most of the time. In fact, the bus on a Raspberry Pi 3 won't even handle that. But if I had a Raspberry Pi that could do 6 gigahertz, then I could send just a smaller amount of data to it, but I'd have a lot more channels. So here they're actually talking about beamforming, what I just explained. And then MIMO again. With MIMO and Wi-Fi 5, you can have 4 channels bonded together, and in Wi-Fi 6, you can have 8. And that's how they get all of this speed that you want out of Wi-Fi. The reality is it's nice, like Wi-Fi 6 will go up to what, I think it's like 2 or 3 gigahertz. And that's awesome. But in reality, who has that kind of internet bandwidth? And remember, in wireless, you're always going to be limited to the lowest, the smallest part of the chain. If I've got this great, 2 gigahertz wireless, and I'm getting actually 2 gigahertz out of it, but it's plugged into a 1 gig switch, I'm only going to get a gig. So it really comes into play for multiple users more than just a single user. Now going the other way, because not only do we have wireless, now we're seeing lots of people that use cellular as a wireless network. The original data network was 2G, and 2G used something called GSM or TDMA, time division multiple access. And basically, your old phones, actually up until to the most recent iPhone, I think, had a SIM card in them. And a SIM card is just a little card that has a number on it called an IMI. And that basically is your phone number and the number that gives you access on whatever cellular network. The newer iPhones use an eSIM, which is kind of interesting, and I don't really know a lot about. I'm kind of about to have to learn that because I got to figure out how to convert this to an eSIM. My phone has got a SIM card in the side of it. And the thing about SIM cards that were nice in the old days is you basically could move your phone number with that SIM card. Like, I don't know what phone you got it, but if yours has a SIM
Yeah.
card, I could pull mine out of here and put it in
Right,
yours,
we could switch phones.
and we could basically switch phones. Yours would have my number in it.
That's what I did whenever I just bought my new phone off there.
Right, you just put your SIM card in it and it worked. So with eSIM, that's going to be a little bit different. So 2G was very slow. Really, all that you could do on 2G was send SMS messages. And when we started sending graphics and things over SMS, it would take forever. It was really low bandwidth. So we then moved into 3G. And 3G is general packet radio services, our edge. You get a little more bandwidth with 3G. They called it at the time high-speed packet access, but it really, by our standards, is not high speed at all. And 3G actually is still out there in a lot of places. Most phones today, I don't think they've got 2G in them anymore, but most phones still have a 3G radio. And if you get out in the middle of nowhere, because of the frequencies that it uses, your phone might actually flip back to 3G. And you can tell your phone will get hot when those other radios come on. So most things have moved to 4G now. And 4G or 4G LTE based on who, what provider you have. This was the idea of using that OFDA that we talked about earlier for the cellular network. Nominally, you can get 150 megs down on it, but really a 20 meg connection is more actual condition. With all of these speeds that you see like on commercials now for Verizon and AT&T and all, and they show we got the fastest network. They are, they're showing the speed they get, but they're showing the speed you get at a fixed point, a certain space from a tower not moving. They're not actually showing what you're going to get in a car going down the road, which is actual usage. LTE-A, for example, 300 megs technically downlink, but 90 is more what you're actually going to get. And the reason of those two standards is because the companies couldn't agree on a standard. This is where you started seeing some of the splits and why not all phones will work on all towers anymore, because they don't all use the same frequencies. So 5G then comes into play, and 5G aims for a gigabit, but it's really getting between 50 and 300. 5G is interesting because y'all all know what a traditional cell phone tower looks like, right? You've got antennas all the way around. 5G uses hundreds of really small antennas, and each of those is in a different frequency band. So instead of you having multiple people on one antenna in sharing the frequency, the idea of 5G is you get one small antenna, but that frequency and that antenna is dedicated to you while you're on it. And it works pretty good, other than, the bouncing around, but the idea is putting more towers in more places. 5G really works better for fixed, but we are using it for mobile. You've just got to put more antennas out there. So, all right, installing wireless. You set up an access point. You've got to run power to the access point, or in most enterprise situations, your access points are going to be power over Ethernet. That means you've got to have a switch that'll run it. I don't know that they put it in the slides here, but be sure and go back. I know we talked about the two different power over Ethernet standards. Do y'all remember them? AT and AF?
I think so.
I don't remember which is which, so I don't want to lie on the slides. One is 25 watt and one is like 15 or something.
Yeah.
Make sure you know the differences. The older access points didn't have as many antennas in them. They didn't need as much power, so they'd use that older one. The newer ones need more power, so they needed that newer standard. In fact, the reason I got that switch over there, that's the older one. And the university had to upgrade as they're getting ready to try to do all these phones. They've upgraded to more power. So, but these older switches don't, these older access points don't need it.
I don't know if I know we didn't talk about AF and AT. We just, because I don't think we called them that. We called it PoE and PoE plus, which is the same thing.
Yeah,
Yeah, and PoE Ultra.
PoE is 15 watts and PoE plus is 25.
and then Ultra is 40.
Was there an ultra?
Ultra is probably not gonna be on this exam because it's new.
But yeah, AF is 15 and AT is.
Yeah, make sure y'all remember those. Because you're gonna see, most likely when you get out there and work with access points, if you're doing any enterprise stuff, you're gonna do PoE because it's just easier to not have to get, it's so much easier to run one cable. Especially if you're gonna try to do an outside area, because then you don't have to run power outside. You just get a good enclosure and you run one PoE wire out there. And you either buy a pre-made cable so that you know you're not gonna get water in it, or you make a good cable and put it in a good enclosure. That's an area where you'd use one of those little jackets, you know, to put on the cable to make sure you don't get water up in it. So then you're going to set up something called a basic service set. And that is the basically the MAC address of the access point. You can put those together to make an extended service set. And an ESS is how you're able to roam from access point to access point. Like, we only have the two in here, one in here and one in 105. There's really not much roaming because most people that are on our network are in this room all the time. But think about the campus network. You know, if you're walking around in the building, other than the few areas where there's not enough signal, you generally don't lose signal. You just move from one access point to the other. And you do that because each access point has its own BSS ID, but they share an ESS. They're all named, what's it named for y'all? Student? I think you're NSU or something. So you're sharing that one network and they're all plugged in on the same network, and that's the way it works. They're actually all on the same VLAN. So when you move from one to the other, they talk to each other and realize you've moved and send you a signal for you to move from one to the other based on signal strength. And that's done again with a service set identifier. So the way that you connect to wireless, your device broadcasts something called a beacon frame. And that beacon frame is just a little packet that has the name of the wireless network you're connecting to in it. In fact, I showed one of the classes last night a device called a pineapple. If we have time when I'm done, I'll run grab it and show y'all. And it fakes broadcast beacon frames and makes an access network based off that name. But that's how when you go home, you automatically connect to your network. Your phone broadcasts a packet looking for that device, for that access point. And when they find each other, they connect. And that has to be done unencrypted. Encryption can take place after that, but the network name has got to be done in the clear. That's why if any of you live in the columns or anywhere or in an apartment where there's a lot of people, if you go look at the list of available networks, you're going to see a lot. Even though your neighbor's network might be encrypted, you're going to see the name of their network because that's got to be out there. Then you're going to look at what your speed and distance requirements are as you're setting up a network. What are the maximum indoor and outdoor ranges that you need? What are the sources of interference? That's a big one. What are the competing wireless networks? Sources of interference become a big one if you're dealing with something industrial. Or let's say you get asked to do wireless at a hospital. Think about the myriad of equipment at a hospital that could potentially mess with wireless. Try putting wireless around an MRI, for example. See what you're going to have to do to deal with that. An example I like to give here with this is a wireless survey. And the idea of a survey is to try to help you map out how many access points you're going to need based off of what you think are going to be usage and obstructions. And these are not foolproof, but they really do help, especially if you think ahead and get things like blueprints to buildings and learn from a personal mistake I made, figure out what the walls are made out of so that you can figure out really how many access points you need. Luckily, most industrial buildings are going to have these drop ceilings that make it really easy to install access points. Like ours is just screwed in, but if you look out there in the hallway, you know, all these drop ceiling tiles are a standard size. They make a tile that you actually put the access point in, and it's got a key so you can just remove it. So next time y'all are walking around out there, like, look, you'll see there's a special tile that each of those access points are in. So a distribution system is where all of these wireless networks connect to your switches. You try to use different channels to avoid interference. Access points use the same SSID and security configuration in an extended service set. Disassociation and reassociation, that is where it disconnects from a network and reassociates. In the process of that, the key gets exchanged. That is actually the weakest point in the whole encryption algorithm because the key's got to be exchanged. In fact, there's a specific type of attack where you send what's called a deauth. You try to get them to disassociate and reassociate so you can grab the key. And then you can take that key and go in with a rainbow table because it is encrypted. The only way to do it is with a rainbow table and brute force it and figure out what their password is. But it takes a long time, assuming they've used a good password. The reason this still works most of the time is most people, unfortunately, use dictionary passwords. The way that most of the companies have gotten around that now, if you go to like Walmart and buy an access point, a TP-Link or 3Com or whatever brand, if you look, most of them have got a preset username and password for wireless. Most people just don't change it anymore. And the password they make is just a random set of characters. So that at least adds a little bit of security to it.
A rainbow table, that's just a list of a bunch of random words, right?
So all a rainbow table is going to be a list of the hashes and their values.
Okay.
They get really big really quick though.
Right, okay.
The longer the password is, the bigger the rainbow table is. Like, I don't remember the exact numbers, but I'll make it up and we can look afterwards. I remember I think a 5-character Windows password using just upper and lowercase and numbers is 197 gigs. And they grow logarithmically. So let's add 1 character to that and it's going to get up to,
right.
And then let's add symbols. So they get huge.
And then like alternating uppercase and lowercase.
It gets really big really quick.
And then
you're not going to do this for a home user, but really something that has become a thing now. If I'm willing to pay enough to get onto your network, I can buy time on Amazon's cloud to build a rainbow table big enough to break into it. This is actually why WPA3 that we'll talk about in a second is kind of coming around. And another thing to know about is a wireless bridge. And wireless bridges are generally just 2, I'm going to call them access points because generally you put an access point in bridge mode that connect to each other and bridge your network from point A to point B. Like if I had a building over here and I've got a building here and I don't have a wire between them, but I want them to be on the same network, I can take 2 access points and put in bridge mode and point them at each other. And then those networks look like they're one network. And bridges operate at what layer of the OSI? 2. So they're going to send what? They're going to send broadcast frames and everything else. Meaning that would be my DHCP server and everything on one side of the network would be fine. It'd send Ethernet traffic. All right, so most enterprise LANs are controlled by a LAN controller. Instead of having where you log into each controller and change things, there's going to be a controller device, either software or some appliance that you do it with. With these access points, I use the Unify app, for example, from Ubiquiti. With Cisco, we've got a unified module. It used to be called WISM. I think they have a different name for it now. But you go in and you make all those changes to the access points in one place. And the reason for that, I think, is pretty clear when you think about it. Imagine if they decide they want to change the name of the network on campus to Demon right now. How many access points do you think are on this campus? I don't know the actual answer, but
more than 1,000.
I bet it's at least 500, if not more. You're probably right because there's areas where we have lots of them to cover, you know,
Well,
there being lots of usage.
yeah, this campus is bigger than LSUS, right?
Yeah,
And you said last night that it took a couple hundred, and then you had to double it?
I had to double it because of the walls.
Right.
Yeah, that was a big problem up there.
Like, does our wireless go run all the way like over to like that, what's that building called? By, is it the basketball, stadium?
Yeah, there's wireless all
Yeah,
over there,
yeah.
everywhere. So anyways, regardless, a bunch. Think about like your access point at home. How do you change the name of your access point at home? You log into the web interface and change it, right? Think about what a pain it would be to have to do that here if you had to log into every single access point and change the name of it.
Wasn't that why they're in ESS?
Even in an ESS ID though, without a LAN controller, you'd have to log into each one individually. But what this controller does is just that. It is where one config file lives. And like all of these on campus use TFTP. Do y'all remember what that is? What is TFTP?
Oh, that's something file transfer protocol.
Right, which one? What's the T stand for? Do you remember? I'm certain this is gonna be on that exam. Trivial.
Trivial.
Trivial FTP is just FTP without a username and password. It uses a different port. So these access points use TFTP to connect to that LAN controller and get a config file every time they're rebooted. So if they wanted to change the name right now on this campus, literally all they'd have to do is change a line in that config file and issue a command to reboot every router on campus. And when they rebooted, they connect up and get their new config file and they'd have their new name. And that's because they're basically lightweight access points. And they use this lightweight access point protocol to do it. And then power over Ethernet here, you know, they mentioned. All right, so ad hoc networks, just be aware of them. There's very little point of setting these up anymore. Unless it's just you want to share a file with somebody and y'all are not on a wireless network. An ad hoc network is just where you take two devices and you build a network between the two of them, not using an access point. All right, so troubleshooting wireless. Most of the problems that come in with wireless are going to be with either distance or with signal loss. You measure signal strength in milliwatts. A negative dBm represents fractional milliwatt values. Basically, 1 milliwatt is 0 dBms. They make programs that will show you signal strengths. Wi-Fi analyzers are great. I know tons of them for this phone. I'm sure there are some for Apple. I just don't know them. In fact, I'm assuming I'll learn some of those pretty soon. But that is a great thing to do if you're going to set up wireless somewhere, even for a friend in an apartment. Go on and look at the wireless and it'll show you what all's on there so you can try to find some free bandwidth. Basically, you know, you can look at your receive signal strength or an RSSI. Up to 65 is good. 80 is kind of at the limit. You're starting to get too much noise. There are lots of different types of antennas, and I'm going to go through this kind of quick because once I get the recording done, I'll show y'all some of these. An omnidirectional antenna is just a standard antenna that receives in all directions. Unidirectional antennas, there's a couple of types of these, Yagis and parabolics. These directionally send the antenna. A parabolic is a satellite dish. A Yagi is, I'll have to go get it. It's in my office. A Yagi antenna is one that basically looks like a TV antenna. You know, the old TV antennas that have the bars coming out on them?
Well, yeah, there's a picture of it up there.
Yeah, it's one of those. Those are very directional. The thing about directional antennas, you can really increase the signal strength with a directional antenna. But like a Yagi is very directional. If you put a Yagi antenna on a wireless network and pointed it, like if I could get up above the trees and point it, I'd get a long ways with it. But you could not pick that signal up 20 feet behind it. because it is directional in the way it works.
There's actually one of those attached to my parents' house. It was there when we bought it like years ago. I don't know what they used it for, but they also used to have a ham radio in the house.
It is
So it's
probably a
probably
ham
for that.
radio one. Yeah, I bet you anything it's ham radio one.
I don't even know if we still have that.
Those are on the right frequencies for 2.4 wireless, if you wanted to do some directional wireless. Insufficient wireless coverage. This is one that happens a lot. You can either add an access point or configure a wireless bridge. You can do repeaters. A repeater, by the way, I don't think we mentioned it, but it just receives a wireless signal and repeats it out on another frequency. This is used in areas where you can't run a wire. Generally, the rule for enterprise or for anything, if you can run wire to an access point, you want to. It's always going to be faster. But if you can't, you can configure a wireless repeater that will take the signal in and then repeat it to pass it on. And you put one of those kind of like halfway between where you're trying to go and where you need it to go. But of course, you're going to have some speed loss because it's got to receive the signal and then transmit it back out. Antenna placement is a lot. Your cable attenuation, the longer the cable is, the more signal strength you're going to have loss. Channel interference. Again, there's lots of wireless out there now, so finding a channel that works. I don't know, these are probably going to disagree with me, but I don't like using the auto channel selection on anything. I kind of just feel like it doesn't do a good job of switching channels. I like to force channels on things, but lots of people leave auto on, especially if you're in a busy area, and let it just try to find a channel to work with. Overcapacity issues, there's not a lot you can do about that other than adding more access points. And at some point, you just saturate the bandwidth. There's nothing you can do about it. We have, like, think about the Coliseum. We've got several access points down there. But when graduation's going on or when there's a game and everybody is in there on their phone and on the network, it's going to be slow. It's just like if y'all go to the Christmas festival and try to get on your phone, AT&T and Verizon and all of them go to a crawl because there's so many people in town on it at one time. Other issues with wireless, reflection and refraction. So this is especially with outside signals. If you are doing long range wireless, which tends to use the same 2.4 and 5 gigahertz that we use normally, because if you use some of the other ones, you have to license it. Or if you're doing like 5G long range with directional antennas, you really got to look and make sure that there's nothing in the way of the signal. In fact, not too, well, I say not too long, I guess it's been several years now. I was trying to help diagnose somebody that was having an issue with wireless, and they were trying to do a cell signal because they couldn't get anything else where they lived. And it worked great in the winter when they set it up, and it quit working in the summer. And what we finally figured out, they had a clear path in the winter, but in the summer, the leaves grew back on the trees. And a cell signal will refract off of water, and leaves are full of water. So they had to move their antenna because it was hitting through the trees and they weren't able to get a signal. And then EMI interference that you can't do anything about. If you live close to the interstate and, you know, truckers get on their CB radios, those just interfere because they send so much signal. There's not a lot you can do about it. All right, so troubleshooting wireless security. There are a couple of types of wireless security. I'm going to mention an old one just so that you're aware of it, WEP. WEP stood for wired equivalency protocol, and it doesn't exist anymore. It is very crackable is the reason it doesn't exist anymore. So then we moved to WPA, and WPA was based on the RC4 cipher. And when y'all take the security class, you'll understand that RC4 is not as secure as it needs to be. RC4 is fairly easy to crack. So it added something called temporal key integrity protocol. And the idea of that was that the key would change in certain intervals to make it more secure. But there's a problem with the algorithm in that the key changes at certain intervals that are known. So it's pretty weak to use. WPA2 came along and it uses AES. And it uses this counter mode cipher block chaining message authentication code protocol, which hopefully you won't have to know. But basically AES is more secure. WPA2 is what you probably have at home. And there are two versions of that. There's WPA2 PSK, which is pre-shared key. That means you all using the same key. You set up a password, or you hook it to a Radius server, like we use here on campus, and it builds a key based off of your username and password. And then WPA3 is coming along. And I am happy to find out they didn't add anything about WPA3 on the exam. But I want y'all to be aware of it because it is something that is coming. WPA3 basically adds some stronger encryption. It is going to use, instead of just AES, it adds a different way to do that AES encryption.
I remember a lot about, there was a lot about WPA on A+.
Yeah.
And I remember AES was always the right answer whenever they were talking about the most secure or something being the most secure.
Yes.
I always wanted AES.
You basically just had to know WPA, TKIP.
Right.
and WPA2.
And you have to know radius and TACAX as well.
Yeah.
TKIP is around because of compatibility. If you have some old device that you need to put on your network, you may have to turn TKIP on. But it's not secure. So if you have to do it, the answer is really put it in a VLAN on its own and give it really restricted access because you don't want to use it. And WPA3 is not supported by everything, but if it's supported, it is more secure. And in fact, here, I knew they were going to talk about that. Here it is, pre-shared key and personal authentication. So WPA2's PSK, all configurations use the same passphrase. It uses a four-way handshake to generate those keys. WPA3 uses this group passphrase, but it uses something called password authentication key exchange, or simultaneous authentication of equals to generate session keys. One of the big things that WPA3 added are these session keys. In WPA2 with the PSK, you all have the same encryption algorithm. So if you're on a PSK network in here and you're on it, y'all can Wireshark it and see each other's traffic. When we do it with WPA3, theoretically, you're not able to see each other's traffic because even though it's based off of PSK, it's added that PAKE key to it, that key exchange. So it's generated a key for you specifically, and that's supposed to add some security to it so that you're using still that pre-shared key, but you're not able to see what everybody's doing on the wireless network. Most enterprises, though, are going to use this 802.1x authentication. And this is that extendable authentication protocol. And it basically uses that EAP over wireless to connect to a Radius server or a TACAX server, one of those. Generally, you need to know the other ones for the exam, but everything you're going to do is Radius because Radius will connect to Active Directory. And if you're going to do this from an enterprise, you're probably going to have them connect to your Active Directory server. You're not going to set up a separate set of usernames and passwords. So you set a Radius server up, you connect it to Active Directory like we did here, and then everybody logs into the network with their username and password. And it uses that network credential to generate the keys. Some other configuration issues, the wrong network, of course, wrong version of encryption. Generally, you don't have to set any of that. You can let it figure it out. Disassociation or deauths. When you're deauth from the network, that means you've disconnected, you got to reconnect. That is one of the types of attacks that can happen. A deauth attack is where you send a specific packet to make the AP deauth and then try to reconnect and grab the session key. Open authentication and captive portals. Do y'all know what a captive portal is? I didn't mention it, but do y'all know what that is? All right, captive portal is when you go to somewhere that has open Wi-Fi and they put that message up and you have to hit the I agree and it's an open network, but you didn't get on their network.
Mm.
Like if you go to Super One, and get on their network. Basically it is the CYA for the business. If you go in there and do something illegal on their network, you've agreed to the terms that they are not liable for it. If you actually read that, that's all it says. Most of those don't have any encryption on it, so you shouldn't expect any kind of privacy while you're on that network. And that's just called a captive portal. Basically, the way those work is you're redirected via DNS to some system, and when you hit OK, you then get directed to wherever, either a separate VLAN. Some will do it with a VLAN. They'll give you one IP address, and then you'll get another IP address to actually get on the network afterwards. And that is a
Long run.
yeah. That is chapter 15. Have y'all got any questions?
Any questions?
Todd, you got any questions?
No, sir.
All right, let me stop the recording, then I'll see what y'all have got.